I have a question for Mark Bonton. You described all of the uncertainties about what I called the players in the drama in my opening talk, and what you called the sort of biology, what is immunity, what is the competition. You didn't mention what is the role of antibiotic selection, but I would add that as well. And what's the importance of heterogeneity of different types of people. So given all of that, how do you kind of think about the problem of using models like these to inform decisions? The last large Midas symposium like this that was held at the University of Pittsburgh Center was on the epistemology of modeling, and there was a lot of discussion there about whether you can say anything when you have lots of uncertainty in your inputs. But this seems like a tricky one. How do you think of it?
Well, at least you have some information, and there is some assumptions that are clear. So that makes it already better than making any predictions without this foundation or this, let's say, underlying model. So that, I think that's the big value of it. Whether you can, I think there was one person, or there were a few on the paper, once predicted that a certain resistance in pneumococci would reach a certain level on the 1st of October in 2007. And they weren't you that? It was you, huh?
Under certain assumptions which were known not to be fulfilled.
So what I always mention in presentation when I give such presentations for physicians, I say, well, the value is really in the scenario analysis and demonstrating how scenarios differ with different assumptions and different values, rather than exactly predicting what will happen. But sometimes decisions must be made, and for example, with the animal-associated MRSA in the Netherlands, these data really helped us to convince people that they should, that they could relax on what we must do to control this problem, and that has been done, and we haven't seen any problems.
Anybody else? If there's not, in the meantime, I'd like, Bruce.
You know, there's sort of an interesting phenomenon about this replacement of strains and the vaccine. We sort of perceive it as if there's this open habitat for pneumococcus, and they're going to fill it with each other. If one doesn't do it, another one will there. Mechanistically, I don't understand that. I mean, you only have some carriage at some time, and what are they really competing for? Why against each other? I just, you know, and this notion of estimating fitness when, as you say, they're all coexisting. So there really is not much relative fitness difference. I'm not quite sure how you put it all together other than say it's complex.
So, I mean, the issue of coexistence with fitness difference. So the issue of fitness difference, I think, if we find determinants that we can explain mechanistically, which correlate with some things being more common than each other, and these are correlated with in vitro measures of fitness and sort of biologically plausible measures of fitness, then I don't have a problem with calling that fitness difference. So then the issue is allowing for a model which has sort of strains of different fitnesses, but which still coexist. And I mean, you can view that different ways, but I guess the ecological perspective is if things are competing sort of slightly more with each other than between each other, then things can coexist even with fitness differences. So one particular mechanism, and the mechanism that I introduced is sort of I think has been regarded and has been studied quite a bit in epidemiology, in pure epidemiology without the multiple strains, as a kind of crude representation or a simple representation of spatial heterogeneity. So spatial heterogeneity allows things to compete with each other, and still, while at a wider scale, some things not outcompeting, being fitter than others. But you know, the fact that we can predict that which serotypes are likely to be resistant, and they actually are resistant when we didn't know that. I mean, this is not a post hoc explanation we put together. We predicted it. I mean, Mark initially predicted it, and then we put it together, and we put that with estimating the cost, and it worked out. So I would respectfully kind of disagree with your proposal on that point. The point about vaccine replacement is interesting, but I think what Bill showed and what Nick showed is that there is something about the strains in addition to the capsule as well. I mean, the 23F strain just keeps on going. I mean, that's completely apparent. It has a phenotype. Which allows it to be quite successful within part of the human environment, and it just switches its capsule and keeps on going regardless. I'm sure Bill would like to comment.
Yeah, I mean, essentially, I have a certain amount of sympathy with you. I mean, I find it difficult to establish mechanistically as well, or difficult to think my way around. On the other hand, it's a pretty robust finding, and it's quite interesting to note that, as I'm sure you're aware, Mark has shown that and others has shown that carrying pneumococcus, remember carriage is a natural state, does not protect very strongly against carrying that serotype again. On the other hand, Mark has also shown a number of other in vitro characteristics which you would expect to be associated with fitness, and they are associated with the things which are more common. And so you would think that that has to be in some way a determinant of success. But the difficulty I always have is coming back and thinking, what about the rare things? Because they're still there. Because, I mean, success is a relative term, because every time we look at this, we should remember that everything we see is actually pretty darn successful, because however many ways there are of being alive, there are infinitely more of being dead. And the thing is that these things are in a competitive environment, and they are somehow managing to do something right. Now, how it is within the pneumococcus that they manage to maintain, that is maintained, I mean, we could talk long into the night, and we probably will again. I wouldn't want to nail my mass to any particular explanation, but I would like to take the opportunity to turn to Christoph, because you made me think of this with your question, and talk to him about gamma, which I think is really, which I'm not going to suddenly start disagreeing with you, but I did think that it was interesting that it made me think of this principle from evolutionary biology about dispersal, which is that for a fit thing in order to be selected and to actually move through a population and become more common, it has to be dispersed into the environments where it will be selected. Dispersal is very inefficient, and that suggests that there would be some selective pressure to ensure the dispersal of bacteria as well. Can you think of any, other than coughing?
I'm not completely sure I understand the question.
All right.
But I think the problem is the problem is not with fitness or with fitness cost, because actually we can make predictive models and really good predictions. The problem is with competitive exclusion. So the problem is that a lot of the models we do have competitive exclusion, and we don't observe competitive exclusion. So that's a challenge, and I think we're sort of part of the way towards understanding that.
Let's say question on the same track is how to differentiate high rates of clearance of high clearance per day. How you can differentiate that from sampling errors of low inoculum?
Do you want to take that?
Do you understand that? So if you have a very small population of, let's say, unusual serotypes, for instance, maybe just by random sampling, you don't detect them from time to time. And therefore, you see, well, it has been cleared. But no, it's not the biological phenomenon, it's maybe just random sampling. So if these strains are not permanently there, it's extremely difficult, if you don't assume high transmission, that these minority serotypes will be still there in the population. So how to differentiate random sampling from high rates of clearance?
If I understand that correctly, I think that at least part of the answer is in that we do get quite large error bars in estimates of the duration of carriage and clearance rate for things which are which are very rare because we just see them very seldom. Do you want to take that forward? Because I mean, I think the uncertainty is very important. I agree.
It has been very difficult to obtain reliable estimates for the duration of carriage of the short duration serotypes, so things like serotype 1, serotype 3. I'm sorry, I don't know all my serotypes off by heart. But the study design, which is a separate study, which is Mark and Anthony Scott, was quite well designed to precisely to try and get good estimates for those by sort of finding people initially in carriage and then following them. If I've said something wrong about that, Mark, feel free to correct. I mean, but there is a lot of uncertainty. But the point is that from our perspective of the fitness cost, the lower bound on those uncertain intervals is high enough that it fits with the prediction of essentially that those should not have drug resistance. So we have a lot of uncertainty, but the data that Mark and his colleagues have collected is good enough to fit within the framework of our predictions.
But I think there is some risk of confounding those, or of confusing those two things. The things that the measures taken by Osman and Anthony Scott to try to deal with that was to define the end of a carriage episode as 2 consecutive negative swabs as opposed to just 1, so that helps a little but doesn't perfectly solve the problem. And the serotypes that tend to get cleared by the immune system, which is to say that have an episode of no detectable carriage, are also ones that tend to be replaced by other serotypes. And so whatever it is, it's an end to detectable carriage, which is something bad about fitness, but you're right, it's very hard to precisely say this is completely gone without grinding up the nose.
And I don't think anybody's going to want to do that. It should also be noted that we don't know anything about the titer of these things. They could still be there, but they're carried in far smaller numbers. So.
There's a long tradition of equating serotype with clone in pneumococcus. Is that really true?
No,
Okay.
it's not true.
The Nick Croucher's study showed very clearly that most of the genome carries on and is happy to take on a new serotype. And I think that 11 events within the history of that particular lineage. Oh, you're just at 10.
Just only 10.
Only
okay,
10.
Right.
10 serotype switches in one lineage over 30 years.
And it does depend a little bit on serotype but for instance, if I think of serotype 1, there are very few clones associated with serotype 1. If I think about 19F, there are gazillions. But in general terms, if people speak about a serotype as if it's an entity, then they are mistaken. And in fact, I would argue that Nick's work shows, among other things, that when people talk about a sequence type as an entity, they are also mistaken. But, this is the genomic future.
But a prediction, therefore, of selection, which would be really nice, would be that if you had a 19F that acquired a 1 capsule or a 3 capsule and happened to be multi-drug resistant, it would then be outcompeted by the serotype 1 or 3 ones, which are drug sensitive, and reverse, that if a serotype 1 or 3 became a 19F through a recombination, it would be outcompeted by the resistant ones, which would be, that would be beautiful. But I don't believe we have the data to really.
Excuse me. I have a much more general point about the question of strain success, which is that there's a lot of emphasis put into working out what genes or genetic elements go into providing a fitness advantage. But to me, that's only half the problem. The other half is how to maintain that fitness once it's been achieved. So it's all very well getting up to an adaptive peak, but then you have to stay on this peak in the face of not just competition from the strains, but from the onslaught of deleterious mutations, for example. So it seems to me that we have to think more broadly in terms of population level effects, whether recombination can help for a strain or clone or whatever to maintain its advantage through increasing the effective population size, for example, and how all that relates also to the epidemiological specialisms of a particular clone. So it's just another way of thinking about success.
I mean, I absolutely agree, and thinking more broadly, so, if I had to speculate as to why these drug resistance do appear to have a stable and long-lasting fitness cost is, there are different strategies. So if Nick showed genomic data from the serotype 3 that have this thick mucous membrane, and they're not recombinogenic. They just mind their own business and just keep on going, whereas the 23Fs and the 19Fs are more recombinogenic. Those are the ones which are drug resistant. And Nick showed, the way it acquires drug resistance is through these illegitimate genetic insertions, and in there they find bits of crap, they find sort of half left over, and there are defense mechanisms for protecting against those bits of crap, and also the sort of selfish genes. But presumably, if you open yourself up to sex and recombination, sometimes you get the good and sometimes you get the bad, and presumably there's a lot of bad for.
I think this comes back to Bruce's point about when they don't do it often, but it can be good, but it's not necessarily. Mark, did you have a?
Yeah, I have a question for you, Christoph. In your model, how did you treat antibiotic resistance? Because we as clinicians still think if the Streptococcus is penicillin resistant, you just can treat it with amoxicillin, no problem.
Right. That's where it gets. That's where things get complicated, and
but you are young and simple, so you will explain.
Simple. And I could see that because for the data we had MICs, so we have the full antibiogram, and then a committee got together and classified them as being S, I, or R, and even that was too complicated for me, so I decided that I was closer to R than to S, though that shows my poor understanding of the alphabet, but still I put I and R together on one hand and S, and I ended up with S and R, but that's absolutely the point. And these breakpoints have shifted over time. So, quite potentially, another way that penicillin resistance could maintain its cost is that maybe the kind of thing that would have been resistant 20 years ago when doses of penicillin or when the penicillinase non-sensitive ones were about, those things have compensated their fitness cost, and what we now call penicillin-resistant ones are ones which have had to go sort of one step further in order to maintain our definition of what's resistant. So there might be a sort of element of shifting goalposts there.
Well, there almost certainly are shifting goalposts, because
antibiotic use changes. I mean, to be honest, we already had a lot of trouble. The data we've got on drug consumption is defined daily doses per 1,000 inhabitants, and we already had a lot of trouble equating that to clearance rates. Now, if I have to, at some point, simplicity has a little bit of virtue as well, because if I had, for each MIC, if I had to put a functional form, a Hill function, I agree with Bruce, would be the best choice. But even putting the coefficients on the Hill function for relating the MIC to different clearance rates for a given daily dose consumption, you have to make so many assumptions that you might as well just shrug and say it's complex.
Are there any further questions? Doesn't look like it. In that case, I guess it's probably wise to take the opportunity to move on to the next session. But before doing so, I'd like to thank all the speakers. No, there are some. Yeah, there are some speaking thingies.
Sorry.
What's it? It's the fast talks about the posters, I believe. Sorry. So thank you, all the speakers.